Good afternoon, everybody. Welcome to the third colloquium in the Heidelberg Joint Astronomical Colloquium series. And this week, we've got a very prominent member of our local community, Andreas Sander, who's going to tell us about his research on massive stars. I must say, this work has a lot of impact, not just in sort of narrow area of observations of stars, spectroscopy of stars, but also in many other things, such as gamma ray astronomy, for example, galaxy evolution. This is a topic which Andreas is going to tell us about, which has a lot of relevance in many fields in modern astrophysics. And in a way, Andreas has been preparing for his role for a long time. He actually did his PhD in radiation-driven winds of hot stars and was laying the foundations of the numerical calculations, which are very challenging, combining radiative transfer with detailed atomic physics and physics of stars. So the PhD was done together with his supervisor. Well, his supervisor was Wolf Rainer Hamann, actually in the University of Potsdam. And in 2016, after the PhD, you stayed there a couple more years, I believe, before moving on to the Armagh Observatory in Northern Ireland, where you, I think, actually then doubled down on this, met some observers, did a lot more work in bringing observations together with the calculations, as well as improving the calculations further. And I mentioned one of your collaborators there, Professor Vink, who actually was one of your external PhD supervisors. This is always the advantage of having external PhD supervisors. So maybe a polite message there to the faculty here to allow those sort of things to happen more often in Heidelberg. But thereafter, in 2000 and well, actually, it must be 4 years ago now. 3 or 4 years. You got selected for the Emma Noether program to lead a research group here, and as you will see in Andreas's talk, there's a lot of very exciting, interesting work, which, as I say, has a lot of impact on many different fields here in Heidelberg. So let us welcome Andreas to tell us all about this exciting new research in what formerly were supposed to be simple objects, but they are no longer very simple, but all the more exciting for it. Thank you very much.
Thanks. So I'm starting here with general concepts to give you some overview on the crucial role of massive stars. So in recent times, we got very interested, of course, in this topic from the side of the gravitational waves and massive stars as the progenitors of neutron stars and black holes. But of course, massive stars also interact with their environment, whether what we call stellar feedback in the form of ionizing flux or the direct mass loss of matter, which then has imprints on stellar evolution. And I could talk about the rest of this slide and its impact for half an hour, but since I wanted to tell you a bit more about the techniques that I'm using, I will skip most of that, but feel free to ask me later if you're interested into that. So if we observe massive stars, we actually observe a zoo of different objects that appear in various flavors. And what we can see here for this in this Hertzsprung-Russell diagram is that a lot of the time that massive stars live in their relatively short lives compared to low mass stars, obviously, they spend as hot stars. So I will talk today only about the hot massive stars. Of course, there are also very interesting science that is done on the cool side here for the red supergiants, for example. But it's quite of a different field that you need, because the physics that are governing the outflows in particular there and the outer layers are quite different to what we need in the field of hot massive stars. So for the hot stars, which is everything hotter than 10 kilokelvin in terms of effective temperature, they have their flux maximum in the UV. They come in various spectral types. And there are lots of open questions on how we connect this zoo. Yeah, you see some exemplary tracks here. But what you already can notice is that these tracks here, for example, go into this region where there are no stars. And they don't go here where there's a bunch of stars, right? So there are various reasons on how to connect that. But we are trying really to understand how this can happen, how these connections are. In order to do that, we need to analyze these stars in detail, because there are several possible paths, but which are real. And we can only do that if we study these different members of the zoo. And to study these different members of the zoo, we really need to look into the details of the star, and we usually need to do spectroscopy, because photometry alone is usually insufficient. If your star is sufficiently blue, so around about 20 kilokelvin or more, you can essentially fit any model to the photometry that you see in the optical. If you play a bit with the reddening, you get every result you want. So this is not enough. Of course, photometry is important. You want to get the luminosity, you want to get reddening, you want to understand if there is a binary companion, for example, but it's very dangerous. And then if you have spectra, maybe somebody took a spectrum some 50 years ago and put you a nice spectral type, you can think, okay, now from the spectral type, I know everything. But it's unfortunately not that simple, because inferring parameters from spectral types is also quite dangerous. Many literature values are from low resolution spectroscopy. And while that might give you some answer, if you look at the star in detail, it's actually quite a different object. And I've put two recent examples here that we studied in more detail and where you would infer quite different things. So for example, this one here, which you would originally classify as an early O dwarf, you would infer a relatively high temperature and even a 60 solar mass star out of that, maybe even more. Now that we've studied it in detail, we find it's actually a binary of two later type stars. Well, not super late, but still temperature is quite there. And then the mass is much, much lower than you would have inferred, right? So you really need to look at your systems in detail. And just because you have some literature spectral type doesn't tell you much. Here's another example, also 40 solar mass star, now broken down into a 7 and a 14 solar mass. So even if you add those up, you are still only halfway here, right? That tells you the need for spectroscopy and for quantitative understanding of the spectrum of the stars. For undetected binaries, and of course the evolutionary status, if you just use spectral types, is often unclear, for example, in the case of supergiants, which can be main sequence stars or quite evolved stars, giving a relatively similar spectral appearance. So how do we deal with this? We want to do quantitative spectroscopy to get reliable parameters. And we usually, if we really want to understand them, we have to not try to take shortcuts via things that we believe should be calibrated, right? So for example, evolutionary tracks, we like to use only afterwards and not to get our mass or our luminosity from an evolutionary track, because this can be affected with some more evolved objects that's just hiding there somewhere in the O main sequence regime. So evolutionary mass is, for example, an interesting thing to compare to, but nothing we want to use a priori in our analysis. So how do we do this in quantitative spectroscopy? Ideally, we have lots of photometry, maybe even some flux-calibrated UV spectra, and of course, optical spectroscopy that gives us a bunch of diagnostics here in this normalized spectrum. And then we want one coherent atmosphere model that fits all of these different features. So something like that. And in this, we didn't just fit individual Gaussians to the lines, but we calculate one physical, meaningful model of the outer layers of the star, then use a radiative transfer to get a synthetic spectrum out of it, and then compare this to all of this set of photometry, right? So this is quite challenging for hot and massive stars, as I will illustrate in the next few minutes. And it also requires a lot of things that we don't talk too often about it, namely atomic data of many species. And in some cases, we're actually limited by the limited amount of atomic data in order to do these calculations or to understand certain transitions even better, right? Something we are just taken for granted often, but really is an important part of the research that needs to get proper credit. Now, for most stars, the effective temperature we cannot get from photometry. I already mentioned that you can essentially fit any model there. So we need to determine the effective temperature from line ranges. The typical thing for hot stars is helium-1 versus helium-2. And when they change, the effective temperature is changing. That's what you see here in this lower panel with this series of lines. And of course, from the line rings, that's probably more prominent, you can get the log G. So you get an idea about the stellar mass if you have a sufficient distance, for which, of course, Gaia helped a lot. On the side of this, there are a lot of additional things. So for early O stars, you have helium-1 vanishing. So you need to, for example, look into the nitrogen lines, which, of course, gets harder and harder the weaker the nitrogen abundance gets. For example, if you go to lower metallicity, you need to look into silicon lines for B stars. And then you need to take into account a significant number of things on top that will affect your profile. And that can also sometimes cause degeneracies with abundance determination. So that makes this a quite complicated process that requires a significant experience. It's kind of an artwork that you learn usually in your PhD times to really do this kind of stuff. And the stuff that I'm presenting today is not just the work that I did, but there's lots of work from my group, where fortunately several people are sitting here who are in the process of learning some of these, or have already learning a lot of these diagnostics, and are then able to decipher all of these interesting things. Finally, not to forget, for massive stars, winds and clumping are playing an important role, and it gives us additional diagnostics. The optical is usually not too helpful there. You might have H-alpha, maybe H-beta, and helium-46 in some cases, but the gold standard there is, of course, UV spectroscopy. And if you don't believe me, you can also believe NASA and the Hubble science team, because they have recently made this very nice plots to illustrate some of the motivations of the Ulysses campaign, where you see this prominent P Cygni profiles in the ultraviolet that tells you, for example, something about the velocity, the terminal velocity of a stellar wind, where you see faster winds making these very broad dips. And if you have weak or even absent winds, then you have almost none of this P Cygni profile. Of course, the UV is also great for tracing the iron in hot stars, because in hot stars above 20, 25-ish kilokelvin, essentially all of the optical diagnostics are vanishing. Everything is too ionized. So you need to go to the UV to get any idea about the iron content of your star. I already mentioned this campaign, so an important thing for our field that gives us the data that we work with in our group. It's not exclusively this, but it has significantly enriched our data set, is the Ulysses campaign. That's about 1,000 HST orbit from a director's discretionary program, half of them devoted to about 350 massive stars. And that's mostly focused on OB and some Wolf-Rayet stars in the Magellanic Clouds. There is a small campaign for low metal dwarfs, but that's really just a few stars, because it's so expensive to look at these very interesting, but also very time-consuming observations in metal-poor galaxies. And the aim of this is formally to create a UV spectroscopic legacy library. That's very important, for example, for people who are doing population modeling. They want proper templates for their stars. But just by selecting targets from the criteria, you once again go back to the spectral typing at the beginning that I mentioned. So it's not clear whether the stars that you think are prototypical are actually prototypical. So what's now a community effort is that we one by one have to go through these things, analyze them, and then see which of them are actually just single. We try to avoid binaries, but of course we still have binaries in there because they were just not detected priorly. And so we need to find the more prototypical stars by a significant spectral analysis. Now, UV isn't everything. A lot of the diagnostics you want to have is in the optical. So what has been done in a community effort led by Yorick Wink is a collaboration that we call X-Shoot-U, for X-Shooting Ulysses, where we have complementary optical data from the ESO VLT. And even the near-infrared, it's a bit more of a headache to use this data because the sensitivity goes down. But we have this all in one goal. And we now have the first public data release with X-Shoot-U paper 2 that was accepted earlier this year. And the spectra should be out very, very soon. And they will also be in the typical archives. So we have made in the community a sophisticated data reduction and a distributed spectral analysis now of eventually all targets. Not all of them yet have people to work on that, and then enables this distinction of prototypical and non-standard objects. Now, I've already talked about binaries. So if you want to have multiplicity, you of course need more than a single snapshot of a star. You want to have multi-epoch spectra. So another campaign that has recently been started and is currently ongoing is the Bloom campaign, standing for binarity at low metallicity, because in particular at low metallicity, there are lots of uncertainties about questions of binaries. So with this further ESO program, we look at 9 fields of the brightest hot stars in the SMC, trying to avoid crowded regions and tackle round about 1,000, not quite, hot and massive stars for 25 epochs between 2023 and 2025. And so the goals include that we determine there the binary fraction orbits for everything that has a period of about 3 years or less. And as a side effect, there are many further goals. We can, for example, find dormant black hole binaries. So these black holes that should be there, but because they're not interacting, they're just hiding in the population and can only be seen, for example, via radio velocity shifts of their companion star. Maybe not as spectacular as what Gaia recently found with the big Gaia black hole 3, but a similar kind of technique that we want to use there. Now, this is the observational side. How do we now get the quantitative measurements? So for the physical roots of quantitative spectroscopy, we have to get back to the basics, thinking about that stars are giant balls of gas. So there's no hard boundary, which means that the definition of a stellar radius is actually often non-trivial. And the spectrum that we see from this star comes from a transition layer, which we call the stellar atmosphere. We have this hot, dense, opaque interior where no light directly escapes. And then around in this regime, light starts to escape and shape the spectrum. So stellar atmosphere models are a fundamental tool of astrophysics to interpret the spectra of stars. And in hot, massive stars, we have particular challenges there. These stars are far outside of thermodynamic equilibrium. So all these nice simplifications with Zaha and Boltzmann that we can use in the cooler star business, we have to let go here. Then we have stellar winds. So this thing is not static, but it's actually expanding, and we have to take that into account in the computer modeling. We have ionization changes throughout the atmosphere that need to be properly accounted for. And of course, we have emission and absorption lines that are prone to multiple broadening mechanisms that we also need to take into account. So this forms a variety of physical and numerical challenges. And just to illustrate that, I've put up some exemplary pictures here. I don't have time to go through all of these. Feel free to ask me if you're interested, but the non-LTE situation, the multiple scattering, the expanding atmosphere, the connection of a hydrostatic regime for the inner part to the supersonic, some effort to define something like a temperature even in a non-LTE environment. And then we have to deal with the fact that we don't just have some simple atoms like hydrogen and helium with a few lines, but we also have very complex atoms such as iron that need millions of line transitions that we need to somehow press into certain energy bins to deal with it, right? So these departures in our business, maybe you've heard of them in the field of cool stars, they are much larger than that business. So we cannot treat LTE as a correction to some solution in the spectrum formation. We need to intrinsically solve the equations, the statistical equilibrium. So we have a high dimensional complex system of equation that we iteratively need to solve. And that means that, for example, abundance changes in one element can affect lines in other elements. So what you can do in other fields, you can just say, okay, where there's more nitrogen, I just recalculate the nitrogen spectrum formation. We cannot do that. Because what you do with the nitrogen might have a small effect on the helium lines or something. Yeah? For the stellar winds, I already mentioned that we need to go to expanding atmospheres. For hot stars, radiation pressure is dominating over gas pressure. So we have a momentum transfer from photons to matter. And this can alter the spectrum. So it needs to be modeled intrinsically from the very get-go. This is subject to instability. Radiatively driven winds are intrinsically unstable. But fortunately, if we look at a star now, and if we look at it 10 years later, for most cases, the spectrum will not have changed significantly. And so there is something like a time averaged stationary solution, which is what we make advantage of when we want to analyze such spectra quantitatively. And if we write down the radiative acceleration versus gravity, we see that there are three defining quantities for this ratio, namely the luminosity and the mass. And there's this small quantity which looks so innocent, kappa f, but it's actually the flux-weighted mean opacity, which turns out to be quite complex to calculate because it's depending on all of these non-LTE population numbers. All right? So if you usually talk about opacities, in a lot of cases, you talk about something that's called the Rosselin opacity, which since the 90s, we have nice tabulated values that are, for example, used in stellar structure calculation. In stellar atmospheres, this Rosselin opacity will not describe the flux-weighted mean opacity. It does the same. They're basically the same in the inner parts. But once you go out into the wind, the flux-weighted opacity significantly is significantly larger than the Rosselin opacity. And the reason for this is that we have a Doppler shift of the lines. So your line can actually absorb more and more flux because it's shifted when the matter is accelerated. So the further the matter is accelerated, the more the frequency of the line absorption shifts. And that allows you to sweep up a whole lot of radiation that you couldn't do in a static environment. So how do we solve this? People have tried to do significant approximation, and you can do an amazing amount by doing that, but it also hits certain limitations. So what I'm doing with the code in my group is that we do basically the most brute force method of that, and that's called the co-moving frame radiative transfer. It's essentially just a brute force numerical solution of the spherical radiative transfer equation. And we use this in the co-moving frame because it spares us the additional hurdle from dealing with the opacities and emissivities being non-isotropic, which would be the case in an expanding environment. Otherwise, typically we have to deal with between 200 and 400,000 wavelength points. It's an initial value problem. You have to start it at one edge and then go through all of these things, which is the end of all the big parallelization efforts that you otherwise do nowadays. And at each wavelength, then you have an equation system coupled in space. And typically, I looked this up in preparation of this talk, we solve about 10 to the 9 intensities for a single model that we eventually want to have, right? The benefits is you have implicit physical effects that you otherwise don't have. So, for example, line overlap and multiple scattering are just automatically taken into account. And you also don't use something that's called the Sobolev equation. I won't go into details here, but it means you get a way more realistic line force. Mainly you calculate exactly this nasty kappa f quite correct as you can do it in a one-dimensional simulation. The downside is that each of these computations with detailed atomic data takes a few minutes. So if you iteratively need to solve this, codes that use this slow-moving frame radiative transfer require hours to days to solve a single model. So you don't just press a button and get a spectrum, but you press a button, you get some T, you write maybe an abstract for your next paper, and then you look how the model is going, and maybe next day the model is converged. Yeah. Now, all of these things are, of course, coupled. You don't just solve the radiative transfer once, but you have a coupling of those, which is illustrated here. So the radiation field depends on the source function that depends on the population numbers, but the solution of the population numbers with these rate equations depends again on the radiation field. So you need to go back and forth to make this work. And this is the reason why you don't just spend half an hour or so, but you really spend hours to days to get your model converged. But in the end, you can get a scheme like that. That's kind of the state of the art for hot star atmosphere models. You put in your stellar and wind parameters, and then you iteratively correct for the temperature, the statistical equilibrium, and the radiative transfer. And once these things don't change the next anymore significantly, then you consider your model converged, and you calculate the emergent spectrum in the observer's frame. So that's then the spectrum that you can actually compare to your observations. And if you find a reasonable thing, you can reproduce, for example, this model, but you can also look, for example, into things like the ionizing fluxes. You can get the SED way beyond the typical observable regime of the far UV. So this is, for example, very interesting if you want to understand what contributions you have to helium-2 ionizing flux. I will come back to this a bit later in this talk. So now let me show you a few examples inside and outside my group that we are doing with these kind of techniques. So for example, one thing that is crucial in this massive star zoo that you saw in the beginning are B supergiants. These are evolved objects, and we don't find them just in our Milky Way. We also find them, for example, in the SMC. So as part of this ICSHUD-U collaboration, one of my PhD students, Mateusz, he's over there if you have questions, as studying these evolved objects, but the raw HRD positions would be inconclusive with respect to the nuclear burning stages of these stars. Yeah. So he performed a combined optical and UV analysis of the Ulysses and ICSHUD-U data to answer, for example, science questions such as, do the ones in the SMC differ from those that we know in our galaxy? What is their evolutionary status? And how do the winds of these stars scale with metallicity? Yeah, they're predicted to be weaker, but what does that mean quantitatively? Right? Here you see a bunch of the models overplotted with the observation. The fact that you don't really see two lines shows that the models are reproducing the observation quite well. And then we've taken a look into these last questions, especially here. Yeah, how do the winds scale with metallicity? This is very important because these B supergiants are in a transition stage where we have a traditional prediction of a break in the wind regime. Yeah? So the typical thing that's included in most stellar evolution models you see here in this upper curve is an increase by about an order of magnitude in the mass loss rate when the stars evolve towards cooler temperatures in the Hertzsprung-Russell diagram. And we want to understand if that's real or if that's just something that this recipe predicts, but that we might not observe. Yeah, so Mateusz has analyzed a lot of these stars here and then compared them to the different predictions, including some that don't predict any change at all and something that predict a more moderate change. And what we find so far is that the best agreement is probably with this recent more moderate prediction, but even that is not reproducing everything that we see there. Yeah, so we are working towards a better treatment of these stars in stellar evolution, because that has consequences on how these stars are then further evolving. For example, the famous supernova 97A was a blue supergiant before it exploded. And at that time, that was a complete surprise And still, the typical single-star evolution models nowadays will not predict that supernovae should come from these kind of stars immediately. So we're trying to really understand how these stars are working as puzzle pieces for stellar evolution. Another interesting stage that you see is when one of the stars already has become a compact object and the partner is still a normal, maybe slightly evolved star. And then the compact object is not quiet, but accretes actually material from the other star. We call this a high mass X-ray binary because the accretion leads to the generation of X-rays. And this is something that my postdoc Varsha Ramachandran has worked on a lot. So for example, this M33X7 is one of the known O+ black hole binaries. So slightly hotter than a B supergiant, but not that much hotter actually. And this compact object accretes here. This yields X-rays, but these X-rays are not just there to be detected, but they also change the donor star as such. So the spectrum that we observe, the wind parameters, they are affected. And we need to take that into account. And this is something that Varsha has done in this study with a phased resolved UV spectroscopy, where we revised the donor parameters with the donor parameters. That was actually the only handle people had on the black hole mass. So if you don't know the donor mass properly, in a lot of systems, you also don't know the black hole masses, right? So then with this, we could actually update the donor parameters, update the black hole mass, and also study the impact of X-ray illumination into these stellar winds. And there's another paper in the works about the famous Cygnus X1, where we actually work on what has been up to Gaia Black Hole 3 so far the biggest black hole in our galaxy. Let's see if it stays like that. Going to slightly lower masses, but still massive stars, we find an interesting regime of so-called stripped stars, because stars that are born in binaries will interact, or a lot of them will interact at some point, and then transfer mass. And what remains is a star that is traditionally called a helium star, but it's just been stripped of a significant part of its outer envelope. And traditionally, people have thought that these stars are all what we nowadays call Wolf-Rayet stars, so relatively spectacular things with emission lines, and that they are easy to see. And we now find over the last years more and more the evidence that not all of these stars will turn into such objects, but a lot of stars will have been stripped a bit of their outer envelope, and then they're hiding somewhere in this OB star zoo. And only by analyzing these stars, we find these missing pieces of massive star evolution. Yeah. So we searched, for example, for suspicious signatures in the UV. Here you see one example. This is the silicon-4. Usually this is a doublet. This is not a silicon-4 quartet. This is just two stars showing their silicon-4 doublet. Right. So this one, for example, caught our attention, and then we started looking into the spectra, fitting them, using not just one model, but two stellar models. And by doing things like that, we've found, in this case, Varsha has found already a small population, and she's looking for more, discovery of intermediate mass stripped stars in the SMC. We had a first report in 2023 where we didn't have UV spectra. Now with the XUDU data, we have 3 more candidates that are confirmed, and the paper is now in a good shape. We received a very positive referral report about them, and so this will hopefully be published very, very soon. This is in particular also interesting if you're not working on these kind of stars, but if you're interested, for example, in population synthesis or in stellar evolution, because with the UV spectra for the first time, we can determine mass loss rates for these kind of objects. And as we see here, for example, for the 2 SMC objects, they have significantly higher mass loss rate than other normal main sequence OB stars of the same luminosity, but they are also way below what would people assume for Wolf-Rayet type stars that would be here in this red band for comparison. We can even go lower to to sub-SMC metallicity. So the SMC is the biggest reservoir of nearby massive stars that have significantly subsolar metallicity, about 20%. But of course, we would like to go further or lower in metallicity, because it means we could go further in terms of cosmic time. So we want to understand how massive stars have influenced the universe very, very early on. And to go even lower, we traditionally had to go to metal-poor dwarf galaxies, but they are quite far away compared to how near the SMC is. So Leo P or Sextans A, this is this early part of the Ulysses campaign that this low metallicity part of the Ulysses campaign that I mentioned. You put tons of Hubble orbits on one single star, and you get it with a relatively weak signal to noise. Now, fortunately, we found a few candidates recently in this paper from Varsha in 2020 in the Magellanic Bridge. So in this stream that connects the Magellanic Clouds, there are some rare O stars, and some of them actually have quite a low metal content. And we are now verifying this with new HST data. So Elisa, who is also sitting here, is analyzing these stars and could confirm that we indeed have quite a low, in this case, 6% solar iron abundance, which is something we're quite excited about. So I've shown you now a few examples. And at some point, you might start to wonder, okay, you've analyzed this, but maybe your code is not the only code in the field, right? There are a few other people who can calculate some models. How does this compare to each other? If you say it's, for example, 6% solar, would other people also tell me that it's 6% solar, or just everybody giving me a different number? Well, we try to address this also as a part of this collaboration effort, because there we bring together the people in the world who are working with this, including the creators of the few codes that exist who can do that. And so we've currently also in the work a submitted paper that does a small blind test between the things, where we said, okay, we pick 3 targets and everybody just do the things you always do with your method. So we're not benchmarking the codes, but we are kind of comparing what are the typical approaches in the field. And the answers are actually quite promising. Yeah, in total, we have 3 different atmosphere codes, 8 different methods. The results is we get kind of comparable parameters, a bit more scattered than we expected. The general outcome is because we're also comparing different methods between very tailored models and also more coarse grids, where you just have a grid of models and just see what from my grid is the best thing, compared to if I fine tune the velocity and the abundance and the spectrum a tiny bit better, yeah, can do these approaches. So the tailored fits, it's no surprising, are generally a bit better. People who are trying to use a genetic algorithm, that also is quite efficient, but the errors are probably too low compared to the scatter that we find between the different methods. And the good news for you who don't care about the details, maybe you can say it's usually okay to combine results from different methods. So you're showing some scatter here, for example, here in spectroscopic versus evolutionary mass, but in general, you don't get dramatically different results if you use different methods. Okay, so now after this rush through the first results, let's take a step back and go a bit back to the method side. Now, so far, what I've shown you are what I would call traditional fits with stellar atmospheres that prescribe both the star and the wind. So in the standard wind description, we assume a fixed velocity law on how the velocity of the wind is increasing with the radius when you get further and further away from the star. This yields, as you can see, for example, here, reasonable fits. There we see these features, these p-Sugni lines that are well reproduced with such a model. But we also know that the choice of this velocity law actually affects the predicted spectrum. So what is the correct velocity law? Formally, we have an independence between what we put in for the wind parameters and what we put for the stellar parameters. And from a physics perspective, this shouldn't be the case, because the physics of the star should dictate on how the wind of the star is actually, how strong the wind of the star is, how it's emerging from the stellar surface, etc., and so far, right? So one thing to go further is that we can try to aim something that one would call a unified model for the star and the wind, and does that give consistent parameters? So I've showed you this thing already, the complexity of non-LTE stellar atmosphere modeling. Now, if we want to couple the star with the wind, we need to add one more equation to this, the hydrodynamic equation of motion, which means you instead get this. And I don't want you to look into all the details, but you can see from the increasing amount of arrows that this gets numerically more complicated and also easier to crash in practice. Yeah, but it can be done. And of course, the calculation time is increased, but you can remove this wind parameters here from the input and put it to this iterative correction scheme, so that you now also solve for the stationary wind hydrodynamics. And this is a nice thing, because you don't just get the velocity field, but you get something via boundary constraint in this case that you are really, really fond of usually, because you can now predict the mass loss rate. So how much mass the star should lose, assuming, of course, that its wind is mainly radiatively driven. Yeah, so we can now start to predict wind parameters from given stellar parameters. So aside from all this spectral fitting and trying to get empirical constraints on the stars, the second part of what we're doing in the group is that we use these models as a kind of laboratory to understand radiation-driven winds. Yeah, so because you are doing this detailed radiative transfer, you can also get a lot of information back, simply because you have included all of this physics in the first place. So here's an example from the famous O supergiant Zeta PUP, where I broke down the radiative acceleration into all of the different ions that contribute to this red dashed curve here. Yeah? So all of these curves are contributing to this red dashed curve. And you can see that it's a multitude of different ions that actually only in its combination yield this red dashed curve. So this illustrates the complexity of the physics that are ongoing into radiation-driven winds, and also means that if you change, for example, the abundance of these elements, this will have an effect on the mass loss rate, but also the terminal velocity of these winds that you are seeing. So in the past, I've done this a lot in my postdoc times in AMA. These efforts started on theoretical insights of Wolf-Rayet stars, because in particular for Wolf-Rayet stars, there's no such thing as a closed theoretical description that could give you the mass loss rate of a Wolf-Rayet star. So what people have used are empirical recipes with all kinds of caveats back and forth, and we're now trying to do this better and also get some insights on how things are scaling, how they are dependent, and what this has, what consequences this has, for example, for the observed population for Wolf-Rayet stars. So what you see here are 3 plots from different papers. You see here the behavior of the mass loss rate versus some gamma E parameter, which is essentially luminosity over mass. And you can see that there is a certain similarity between the curves and a certain scaling. So you can try to gain an intrinsic recipe for that to describe what we call classical Wolf-Rayet stars. So these are helium-burning Wolf-Rayet stars. We can also see that these stars actually cloak themselves in a quite strong optically thick atmosphere. So what you see here in green is the actual radius up to which the star can be more or less described by a hydrostatic model. And then you see the radius here as a function. This is a series of models, as a function of mass loss rate versus radius in this case. And you can see here now how the radius is getting larger and larger, the larger your mass loss rate. So basically, the more mass you lose, the more thick your wind will get. And the radius that you instead see is significantly increased here, almost a factor of 10. And so the difference between, for example, what some people call this dynamic inflation, is that a star that would, without its wind, have an effective temperature of about 130 kilokelvin only has an effective temperature of 50 kilokelvin if you look at it. So that's a significant difference in the temperature. And that's something we are trying to map and understand, because it's very important to place these stars properly in the Hertzsprung-Russell diagram and also understand the evolutionary context, of course. Yeah? So we've learned quite some interesting things here, that they are launched quite deeply in the optically thick atmosphere. They are scale fundamentally different than OB star winds, even though they're both radiatively driven, they scale quite different. There's a surprisingly shallow metallicity scaling once you reach this dense wind regime. And there's a strong L2M and metallicity dependent breakdown, which is what you see here. Right? So this looks more moderate, and then whoop, suddenly you're losing the ability to drive, and the mass loss gate goes almost a race to the bottom. Yeah? This has consequences for observed Wolf-Rayet populations. And we also have some recent scaling with the critical radius as well that I don't have time to go into further. Now, this was theory, but how does this look in terms of observations? Yeah, so here is an example from Roel, one of the other PhD students sitting in the audience, where he is trying to reproduce one of the well-known Wolf-Rayet binaries, WR140. You might remember this picture here from the news from JWST, where you see this dust rings. Yeah, so this is a binary where we have mass constraints from the orbit, because people have studied this system for quite a long time. But there's actually not a really good spectroscopic fit to this star. So knowing some of the parameters, they are quite a bit uncertain. And now we're trying to do this with these hydro models, because now we have an independent mass constraint, and we can try to fit this spectrum. You can see, well, not perfect, but reasonably good. We can try to fit this. That's not the fault of Roel. Don't blame him. Yeah. That's the tricky bit of how these winds and how they are complexing. If you look into my my diploma thesis where I started working on this, the fits look way worse. Yeah, so don't worry. But you can try to understand this and then see what mass do you need to put into your model. Does this agree with the orbital mass? And if not, what does it tell us about the physics that are ongoing, that are happening there? We're also doing this in other regimes. Here is some more work from Roel and also from Matthias on different regimes, on later type Wolf-Rayet stars, and in this case, B hypergiants. So we probe radiative driving in quite different wind regimes with these kind of atmosphere models. And the good thing is that these hydrodynamic models coupled to the stellar mass, which in some cases, like here, we have orbital masses. In stars like this one here, which are in the galactic center, no chance. You will not get an orbital mass if this star is not sitting in an obvious binary. So the only way to get to a stellar mass is from spectroanalysis. But if you have emission line stars, you don't get log G from it. You can put any mass in the model, in a standard model, you will always get the nice spectral fit. In these hydro models, the mass is coupled. And so we can now get some unique insights into how massive these stars really are. So far, these masses have been predicted from luminosity. But again, we are then assuming theory. We are making assumptions about what is their structure, what is their evolutionary status. Yeah? The more we can do this spectroscopy intrinsically, the better we can test and compare with theories. Yeah? All right, I promised you to talk about ionizing fluxes. So let me say a few words about ionizing fluxes. The first, one of the most important messages of this talk, maybe hot stars are not black bodies. Yeah? So the opacities in the stellar atmosphere, they change the spectral shape, and there's a strong blanketing effect, especially by the iron line opacities. So if you look into this here, yeah, flux versus wavelength on a log-log scale, you see this doesn't really look like a black body. You can say, yeah, oh, I can cut a bit, yeah, okay. But depending on what you want to know, especially fluxes beyond a certain edge that are able to ionize matter around them, you really need to look into proper atmospheres. And then you can calculate, of course, these ionizing fluxes beyond the hydrogen edge or even beyond the helium edge. The recent one is also getting quite some attention with JWST because people are often referring to POP3 stars in order to explain how helium ionizing photons can be done in the very early universe. So we can take plots like this, we can do calculations, and what we see is if we gradually climb up the main sequence towards higher main sequence masses, we will see that we need to go to the hottest stars at all to get a significant flux here in this orange region to get this helium-2 ionizing photons. These other ones here, these are orders of magnitude lower, and they will hardly contribute. Even this one is not a really strong thing. Okay, these are dwarf stars. Now, what about giants? If we go to supergiants, this doesn't change much because the temperature dependence is the strong thing here that makes this flux. The giants, they will scale this up a bit, but 32.8 is still orders of magnitude away from the 49 or 47 that you might need to do something. Now you could think, okay, I need hot stars. Let's go hotter than the main sequence. What about Wolf-Rayet stars? I just told you, I showed you this example with this 130,000. Yeah, they are quite hot. Yes, they are. But the problem is their strong wind is also the downfall of their radiative, of their strong ionizing flux. Yeah. Here is an example of a WN5H star in the LMC, one of these very massive stars, remarkable high luminosity, basically negligible contribution in helium-2 ionizing flux. Instead, you can only use those stars which have thinner winds. So you can use Wolf-Rayet stars, but you need the ones with relatively thin winds. So for example, this guy here in the SMC has a thin wind. It has about the same effective temperature. So if you try to compare that, lower luminosity, it's still high, it's still a million solar luminosities, but much lower than this guy. And it has orders of magnitude higher helium-2 ionizing flux. So these things are the stuff that you are looking for if you look into ionizing sources, also at lower metallicity, for example. So generally, we can learn from this earlier spectral types at lower luminosities are better sources of helium-2 ionizing flux. But it's not obvious from the optical spectrum because what you look into is usually this regime here and not this one, right? So only the stellar atmosphere model then tells you that. And ideally, you want to have observational constraints, but you really need to go to the UV in order to see what is really going on. So we have actually some approved HST observations that are ongoing this year to do a more systematic study and do this for a few more sources. One thing, if we combine this again with our theoretical insights, is that we can try to calculate different model atmospheres for different conditions. And this is what's been done, for example, in this paper. And we see that there's a relatively general trend how we can scale these curves with something that we call the transformed mass loss rate, where then almost all of these curves align. So this is really nice, because if we are able to calculate such a quantity, we can see whether certain stars should be strong sources of helium ionizing flux or not. Yeah. In the last few minutes, let me go a bit on the larger scales, massive stars and stellar atmospheres in population synthesis. Massive stars also dominate the light of star-forming galaxies, which makes them a crucial, means there is a crucial role of atmosphere models in spectral population synthesis. Once directly via their spectral templates, and second, because of the strong ionizing feedback and chemical enrichment. Yeah. So if you put all of this in the big population synthesis machinery and get your large-scale quantities, you still are dependent on stellar atmosphere models and the individual assumptions made there. One thing that has gained quite some attention are the so-called very massive stars. So these are stars typically with an initial mass of more than 100 solar masses. And for these stars, the spectral appearance changed from an O-type star to a Wolf-Rayet type star, or officially a WNH type star. So you have this spectral transition on the main sequence. That's simply because the stars are getting closer and closer to the Eddington limit. And so it's easier to drive a strong outflow. And these stars are formally Wolf-Rayet stars, because Wolf-Rayet stars are formally a spectroscopic definition. But they are hydrogen burning. They are not helium burning. They are not evolved objects. They have 60–70% hydrogen in their surface. And they have nowadays been detected up to redshift 3 in star-forming galaxies. The question is, of course, these features will get weaker when you go further away, and also if you go to lower metallicities. So the Z dependency of this is a non-trivial thing and something we are very interested in, because it makes a difference in the early universe. If you think about stars that could enrich galaxies, for example, with nitrogen, these things are really nice candidates, but we need to figure out if the math actually works out. Yeah. Why are they interesting candidates? Because they are not just getting this appearance, they are also showing an enhanced mass loss compared to how O stars scale. Yeah? So that's not yet included in most population synthesis models. You can see this here in this paper from one of Yorick Wing's PhD students that I was also involved. You see here the trend for the O stars. And then at some point, you switch to this optically thick wind regime, and then you scale even higher. So your mass loss rate doesn't just go up, your mass loss rate goes up even further than what's expected from the O star regime. How this scales with metallicity is an open investigation. This is from a first study where we try to explore that a bit further. And these very massive stars yield 5 to 10 times more hydrogen processed elements, so especially nitrogen, but also neon, sodium, and aluminium. And they could be, I'm speaking very carefully here, a source of early nitrogen enrichment in the early universe. So interesting for objects such as GNZ11, but also globular clusters where you have this impact of nitrogen in the second population. Yeah? Notably, they will not contribute to this helium-2 ionizing flux if they have these strong winds. Yeah? If there's something like a break-even point, something we need to figure out, but the strong ones will not give you the hard ionizing flux. Okay. So in the last parts, a few others that we're also involved with, we can couple our stuff with simulations that colleagues are doing, for example, here at MPIK, and this is what Cormac is doing. One of my PhD students also sitting somewhere in the audience. There he is, who is involved in the supernova simulation, where we then plug our insights on how these stars are evolving into a 3D MHD code, and then try to, in this case, determine the potential of young supernova remnants as cosmic ray accelerators. From a structural perspective, Joris, who couldn't be here today, is trying to connect this between structure and envelope. So because everything I've talked so much about is from an atmosphere perspective, but it's actually not a trivial thing how to connect that to the deeper layers of the star if you have this moving material, right? If you have this wind outflow and you launch this very deep, you're actually launching deeper below than what you can see. And so for these kind of stars, the question is non-trivial where the hydrostatic part is ending. And the evolution models typically make very strong assumptions and simplifications, even ignoring certain terms because they don't want to handle them in various codes. And we are trying to do a better coupling to better understand this, because we have severe discrepancies sometimes in the temperatures that we predict from stellar evolution and that we determine with our spectral analysis. And in order to resolve that, we really need to work better on this structure and envelope coupling. Now, all I've shown you so far in this talk is 1D stellar atmosphere model. And it's 1D because the radiative transfer is already so complicated and all this non-LTE that we need to treat that we usually cannot go into 3D. But of course, our stars are not perfect spheres. So we have to do something. And what we are doing is we're collaborating with some folks in Leuven who can do 3D simulations, but then at the cost of approximating a lot of the physics that we treat in more detail. So here are some snapshots of time-dependent simulations, and you get then not just one velocity, but some velocity distribution and an average profile. And Gemma, who is here as well, is working on trying to see how we can bridge that into our detailed 1D calculations using the insights from the 3D simulations. Yeah, so one project that that she's working on currently is the 2D O-star models by Dvaipayan, who predict significant motion below the photosphere, even in O-star models. Yeah, so far we thought O-stars were easy. No, unfortunately, they are not that easy as we think. Yeah, so for higher subtypes, especially, you find significant motion that you can try to approximate as a turbulence term. And we're doing this here, and with some playing with this parameter, we can actually fit reasonably well the averaged 3D, or in this case, 2D density structures with different models. But the interesting thing is, and I didn't have the time today to put more slides into this, this will affect some of the diagnostics, how you determine log G. So your log G, for example, will change if you add turbulence into this whole game, right? We can do the same thing also for Wolf-Rayet stars, where we also have the 1D stationary terms. And here it's a bit harder for the velocities, but we can once again see we can reasonably well reproduce the density structures. We cannot get this non-monotonic part here, but we can qualitatively already get quite some nice agreement between the 3D and the 1D model. So just to summarize, this is the team that has worked on a lot of the stuff I've shown you today. But massive star atmospheres, and especially hot star atmospheres, have a quite manifold role, and that's what we are trying to address here in Heidelberg. Spectral analysis is our basic thing. The further development of the atmospheres is a central role. We are trying to investigate the theory of radiation-driven winds. That, of course, is inherently tied to stellar feedback. With this, we can create stellar libraries going all the way back to the first population of stars, the POP3 stars, trying to couple the structure and wind envelope, and also provide things for larger simulations, for example, MHD simulations. And with that, I'm very happy to take your question, and thank you very much for your time.
Oh, thank you very much, Andreas. That's a really remarkably detailed analysis, and it looks like it's producing a lot of very interesting new results. I'm sure there'll be questions on this. So I'll open up the questions to the floor first, and then if anybody online wants to ask a question, put your hand up and or type in into the chat, I want to ask a question, please. Okay, so questions from the floor. Everybody's thinking still. Can I ask a question, Jen? Yeah, I find it fascinating, the effect of these optically thick winds on the ionizing flux. So you get a much higher ratio of kinetic energy feedback into the interstellar medium as opposed to ionizing radiation feedback into the interstellar medium. Presumably, you said this was some function of metallicity, right? But is this going to change anything significant about our understanding of stellar feedback, for example, in very early galaxies compared to local universe galaxies?
This is a good question, and I cannot give you a final answer because we haven't included new models into this population synthesis.
Yeah.
What we know is that the biggest difference is on this harder ionizing flux, right? So for the helium-2 ionizing flux, where you need to assume or where people so far needed to assume a wind mass loss rate. And if they assumed a too strong mass loss rate, they will just suppress these flux. So if the mass loss rates are lower, you will get more of this stuff out. On the other hand, to get to this regime, you also need to have the star losing a significant amount of mass. Of course, this could be done via binary evolution. So maybe you don't need the self-stripping via the stellar winds, which has been traditionally assumed in most simple stellar population models. Yeah. But you would need to have an additional mass loss mechanism that then takes you to this regime that even if you have a not too strong wind, you can get a lot of hard ionizing fluxes. So this is all interwoven, and that makes it hard to give you like the one thing, but there is quite some potential.
Yeah, I mean that question of the binary stars. I mean, we've heard that most massive stars are multiple systems. So that was actually another question I would have had. You know, the actual dependence of the sort of at large distances, the kinetic energy input on the binarity of a system, because presumably, you know, along the polar axis between the two stars, things don't change so much, but along the equatorial axis, you'll have gas colliding, thermalizing some radius dependent on the separation of the stars. And potentially, I would have thought that might affect the kinetic energy yield. I mean, do you get what I'm trying to say? I'm probably expressing it very badly, but
are you know, talking about
colliding winds, you get a thermalization of the wind, and that will affect the kinetic energy output.
This will be a bit of an effect. It depends on how extreme the system is. Yeah, if you have, I talked about the high mass X-ray binaries, which is not a colliding wind binary in the classical sense, but it's still a binary where the donor is affected. I wouldn't say that in the systems we know it makes a dramatic impact. It can have some impact if you irradiate, but if you do, for example, X-rays from colliding wind binaries, or if you have something that's called radiative braking, you see a bit of an effect, but it will usually not change the overall conclusions of the systems dramatically.
Okay, so questions from the floor? Yeah, I see one from Keystones. And one over here. Who's first?
Yeah, so I have maybe a bit of a technical question, and just maybe because of my ignorance, but line-driven winds, you need at least a certain separation between the lines. Otherwise, at some point, the lines overlap, and you can't get more photons from the star than there are, essentially, right? So does that play a role? Does the line-driven wind essentially get out of steam because at some point the different lines start overlapping?
That's actually a good question. It's very difficult to answer this on a model by model case, because we are not really writing out all of these details for every model. But yes, it plays a role. So if we wouldn't include line overlapping, we would get a different answer. And one of the reasons why we are doing co-moving frame calculations versus, for example, simpler Sobolev approximation is to have this line overlapping effect. And what actually happens is that when people did comparison between Sobolev and co-moving frame is that the co-moving frame force is lower. So one of the reasons why originally people assumed slightly more efficient radiation-driven winds is because they made these simplifications, they ignored overlapping, and then it all worked so well. And when people did the physically more correct thing, they see that in certain regimes, actually this is not sufficient anymore, and the force that you get is lower. So it plays a significant role. And we see actually both phenomena. We see phenomena where more overlapping is harmful, and we see phenomena where the inclusion of additional elements has opened new opacity windows that could be absorbed. Yeah, so this is the problem. We really need to get everything right. And we are usually calculating about 2,000 explicit levels. So in a lot of cases, we need to do iteratively. We throw out those again, which we are seeing are not important, and then testing others because we can't do the full bunch in a single model.
Okay, there's Fabian Schneider has a question.
Well, Andreas, thank you very much. Extremely rich talk, and I probably have many questions to many topics. But let me start maybe with two items. So you presented this little comparison study of different atmosphere codes, and then you said essentially there are no systematic differences. So in my memories, and they might of course be outdated or maybe just is not correct anymore, there was always a issue with the log G of, I think it was CMF gen versus fast wind models, and there seemed to be always a systematic offset. So I would like to hear more about that and whether it has sort of disappeared and it's gone away. And the other question would be on your high mass X-ray binaries. And this was extremely interesting. And of course, you alluded to the Cygnus X1, and I was wondering whether you can say a little bit more about this.
Okay, let me start with the comparison. Of course, if you talk, I think one of the good things in our community is that usually the creators of the codes are also the most critical persons of their own work, which is a good habit. So if you would ask the creator of FastWind, Joe Puls, he would probably say that there is still an issue in certain parameter regimes. What we've seen here is that if people do their usual business, you don't really get dramatic differences in log G. But actually, one thing that I didn't talk about here, that we have a small remark in the conclusion, and Joe actually asked me to squeeze that more because I was a bit reluctant on putting this too prominently, is that we need to think about this turbulence term in the hydrostatic equation. And we looked into the difference between spectroscopic and evolutionary masses. And the only code that does this turbulence term is actually power. So it's also in Telasti, but it's not in CMFGen or in FastWind. And so the power models seem to be a bit better in reducing this mass discrepancy by including a bit of this turbulent velocity. So this is preliminary. It's not systematic, but it's one of the outcomes of our study that we see. We need to look into this deeper. Between CMFGen and FastWind, I know there's this bake-off paper, and probably you have to ask the people of that paper how much that still stands. At least here we've seen there will be differences, but it's not that you have a 30 solar mass star appearing as a 50 solar mass. Yeah. Regarding the high mass X-ray binaries, the Cygnus X1, I cannot say much more. The black hole mass is not going to change dramatically. This is probably what you want to know. But the parameters of the donor star actually change quite a bit. So this has to do with the fact that people in the past have used simplified codes to study the donor star. And just out of pure luck, they got the black hole mass better than they usually would have gotten.
Okay, good to know that luck's still involved somehow. Well, I think we're running a little bit over time, so I'll draw things to a conclusion. I don't see any people online who want to ask a question. Before we thank Andreas, I'd like just to show one slide to advertise next week's colloquium, which will be by Anja van der Linden, and we're going to go into cosmology, and it's one of the big topics of surveys of massive galaxy clusters have been, what does that tell us about the evolution of the universe? And Anja will get us up to date in that very interesting topic next week. If anybody wants to arrange to meet Anja, she will be here for, I believe, 2 or 3 days around the talk. Get in touch, please, with Joachim Wanscans. So with that, we will not have a dinner tonight because it's a local speaker. We all know where we can find you, Andreas. I think there's a lot more questions to talk about, but thank you again for this extremely comprehensive overview of your very interesting work. Thank you very much indeed. Oh.